All right, do we want to get going?
Hi everyone, welcome to Quasi's 2017 Spring Cyberseminar series. It is on heterogeneity, complexity, and anomalous transport and hydrologic systems. It's hosted by Diogo Bolster from Notre Dame University. My name is Liz Tran. I am the Community Relations Specialist here at Quasi. Just wanted to let you know, if you have any questions during the presentation, please type out your question in the chat box and we'll answer it at the end of the presentation. So take it away, Diogo.
Okay, so welcome everybody to this series of 4 cyber seminars. I hope they'll be interesting. Today, we're lucky enough to have Rina Schumer from the Desert Research Institute talk. One of the reasons I asked Rina to give this first talk is I think she's somebody who's worked in anomalous transport right from the get-go, but really explored and looked at it not just within the context of groundwater systems or surface water systems, but really looking at areas that we don't always necessarily think of as hydrologists, and I think it's important to think about them. So I'm excited to hear what she has to say and how she's going to put this forward. And so without further ado, Rina, I'll give it to you.
Okay, thanks Diogo, and thanks to everyone for tuning in on a Friday afternoon. I don't think anyone said the title, but it's not normal. Anomalous Transport in Hydrology, Hydrogeology, and Geomorphology. Let me start off with a quick nod to some funding agencies and collaborators who I worked with for my contribution to the topic of the webinar, which is anomalous transport. Of note is that some of the hydrologic applications of anomalous transport that I will discuss were kicked off at 2 early Quasi summer institutes. Some of the collaborators listed below are now postdocs and faculty, but were graduate students at the summer institutes that were led by Siva Paulin, Aaron Packman, Paul Brooks, Marwan Hassan, and a few others. Let's see. Let me also point out that this talk is really in the form of a review. I went through quite a bit of the literature to make sure that I'm up on current events across anomalous transport applications in hydrology and geomorphology. So I'm going to discuss quite a bit that represents the contribution of others. There were references listed in the talk associated with certain figures that I lifted from people's papers, but putting in references to all the topics could take up the entire, the content of all the slides. So I think what I'd like to do is when we post the webinar, I'm going to add a list of references by topic that people can check out. So my apologies to the long list of people whose work is discussed here, whose names may not be shown on the slides. All right, so our topic today is transport and models for transport. I will focus on transport of water, solute, nutrients, sediment, but from a theoretical perspective, I could just as easily be talking to biophysicists, material scientists, econophysicists, astrophysicists, on, because as long as we are talking about regimes that are not too turbulent, the same mathematics are used to describe how things spread. And this is particularly important point because if you're working in the area of transport or anomalous transport, you would do well to peruse the literature in other disciplines. Quite a bit of the theory I'm going to talk about has been developed by hydrologists and other geoscientists, but much of it has been technology transfer from the statistical mechanics literature. So good to know that it's out there. So, okay, on the left here is, let me get my pointer over there, really the only equation that you're going to see in this talk. It's the diffusion equation, and it's the place that we always start for describing the spreading of particles, whatever those particles may be. As I will discuss, there are some applications where the flux of some variable might diffuse or disperse on its own, but in hydrologic applications, there's no dispersion or diffusion without some kind of advective driving force. So I show an advection term or an average velocity term here on the right, but it's not really going to be the focus. Anyhow, we see some kind of diffusion type term or equation when we're talking about groundwater flow, where instead of a P, we might have a head term here, or it might be concentration in the advection dispersion equation, it might be the Exner equation, but the list of applications on the right is here because these are all areas in which diffusion-based transport models really don't reproduce the relevant features of transport, or maybe if we try to use diffusion-based equations, we suffer from some kind of scale dependence, which I will discuss shortly. Just to start at the beginning, I just want to talk about the way I learned the diffusion equation, and it looks like this. We have some kind of constitutive equation describing particle flux. It says the flux of particles is linear proportional to a gradient, so particles go downhill or down energy. If we plug this equation into conservation of mass, we get here the diffusion equation. Turns out there's a whole lot of things that when I first learned the diffusion equation that I didn't learn about, and that has to do with the fact that there are a lot of assumptions about particle motion that go into this Fick's law equation for particle flux. And similarly, although we tend to derive conservation of mass in our transport classes, in either hydrology or some kind of contaminant transport class, turns out that there are a bunch of assumptions in those derivations that are also easily violated. And so this talk is going to cover what some of those assumptions are, and that's how I'm going to define the difference between normal and anomalous transport. I'm going to talk about how those assumptions get violated in a variety of hydrologic and geomorphic systems. And then I'm going to follow that up with a little bit of discussion, which I hope you can join in on the end, about what this means for ancillary hydrologic geomorphic processes, and also, as Diogo asked me to, why it is that anomalous transport has not really gone mainstream. All right, so since anomalous transport by definition is that which is not normal, let's start with what normal means. So when I talk about normal transport or anomalous transport of particles, a particle can represent any quantity that we're transporting. So it could be solute, sediment, the Earth's surface, bacteria, water molecules, whatever you want. I'm going to show you a movie of 5,000 particles here on the middle here, and they're going to be making some kinds of quasi-random motions and spreading as they make those motions. I will tell you now that although they're random, they're still going to be following some very specific rules of what kind of randomness, what kind of random motions they're allowed to make, and I'll go into detail about those. But as the particles disperse, I'm going to track the way in which they spread. I'm going to track that in two ways. The first is I'm going to, in the middle graph, you're going to see a plot evolve of the particle distribution across the x-axis. Right now they're all sitting at 0, so you just see a spike around 0. And then you're going to see that change as these particles spread. And then on the right graph, I'm plotting the mean squared displacement, which in the case of spreading around 0 is the variance of how far these particles travel with time. So with each time step, I'm going to compute the variance of how far things go. Now I know for whatever reason my computer likes to pause this movie in the middle, but just bear with it. There's the pause. I'll take this time to tell you that some of this code came from Brett Sanders' class website at UC Irvine. Anyway, so here the particles are. They're bouncing around. They're moving randomly. And as they spread out, the distribution spreads from 0. It's symmetric, and it starts to kind of look like a normal probability density. I'll do that again, or a Gaussian curve. And similarly, on the right-hand side, what you can see is that this mean square displacement that's computed every time step follows this very nice line. What we see on the left here is the microscopic motion of particles. What we see on the right is what we call macroscopic or bulk, some kind of time-averaged observables that we can measure. All right, so what is the definition of normal transport or diffusive transport? Number one, we have that the spread of particles with time is looks like the solution is a Gaussian or a normal probability density function. Normal means this normal right here. It does nothing to do with abnormal. This is where it comes from. The second definition is that particle spread, the variance of how far particles are moving, grows linearly with time. And that's what you saw in this graph. We saw mean square displacement grow as a nice line, and I'm going to call the slope of that line 2d, where d is this dispersion or diffusion coefficient we see in the diffusion equation. There, I'll say it again, just so you know, if you don't follow these two rules over here, then you have anomalous transport. It's actually kind of a long list. So, to get even more defined, anomalous transport is, you know you have anomalous transport when you've got a solution describing the spread of particles that is not Gaussian or not normal. And similarly, when the growth of the mean square displacement is not linear with time. Now, of course, there's lots of different shapes I could put in here that are not linear. I could put in a polynomial, but in general, when we talk about anomalous transport or anomalous diffusion, we're typically talking about mean square displacement being proportional to some power law of time. And this power, this alpha, this scaling parameter right here, when that's 1, we get back to normal diffusion. When it's greater than 1, we call it super diffusion. When it's less than 1, we call it subdiffusion. So just as I had that schematic before of how we, derive the diffusion equation, we've got something similar when you're deriving anomalous or normal transport equations. A little bit of a messy slide. I'll walk you through it. First, let's remember that we're talking about particle motion, the way solute particles in groundwater in a river, sediment particles might spread around some average speed as they're moving downslope or downstream. We know that what we really have is deterministic motion. If we could do a force balance on every grain, all of these macroscopic transport models that simulate bulk behavior would be moot. But since we generally can't make those measurements, the small-scale force measurements, we typically describe the motion of particles using the statistics of particle motion. It could be one particle at a time, or the statistics of a lot of particles. And we kind of assume that we can make some time steps, and we can say during each time step these particles make some jumps that we can describe statistically. The sum of those jumps tells us about how far these particles move. And the statistics might also describe the frequency of those jumps. And I'm calling this the statistical conceptual model, kind of our discrete analog to Fick's law that I showed you before. This gets plugged into a conservation equation. In general, it's actually a conservation of probability equation known as a master equation. And then when we've plugged in the statistics of particle motion into this equation, we get what we call a discrete stochastic model. Discrete just means we haven't taken any limits to get it into a PDE form. And I mention this discrete point because there are a lot of times where we really just use discrete stochastic models to simulate anomalous transport. One of the popular ones is called a continuous time random walk, and we've got what's called the Scherr-Montrol equation in here. But in many applications, we actually take a limit and we end up with some kind of partial differential equation called the Fokker-Planck equation, the best known of which is our diffusion equation. There's lots of others. But in order to get this particular equation, there are a number of requirements, as I keep saying, on the statistics of particle motion. And here they are. So when we have our particles bouncing around, there's a few things required. First of all, the way each of these particles moves has to be independent of all the other particles. If things get too crowded and they start to hit one another, the assumptions needed for diffusion get thrown off and you'll end up with something else. We also need, for some given delta t or characteristic time scale, the displacements that these particles make need to be independent of one another. So that's the steps that a single particle makes in a given delta t. Right? So what happened a few time steps ago cannot be relevant to what is happening right now. And similarly, at that time scale, we have to be able to describe these particle jumps with a mean and variance. And you might think, well, give me any bunch of numbers and I can calculate a mean and variance. But it turns out when you have collections of numbers, or you have a bunch of things that are statistically described by, say, a power law distribution, with every subsequent step, it's so likely that you might see some kind of, some size that you haven't seen before, some new piece of heterogeneity you haven't seen before, that mean and variance simply, as you calculate them, they tend to change, and they're statistics that don't work really well for these. So how do we violate these? Well, there are a number of applications, mostly in biophysics, where we might lose this independence of individual particles. Really crowded environments, or in polymer physics, they look at single file trajectories where particles typically can't keep going because there's a particle in the way. This statistically independent displacements requirement can get violated when you have correlations in, say, velocity fields or the length of time for which particles will be immobilized. And this well-defined mean and variance requirement can be violated when you end up with power laws. And that's why we see so many power law posters and stuff at AGU, because they make a big difference in terms of long-term transport. When you have power law velocity distributions or periods of, or immobile periods, you violate this assumption. And take a look, there are a long list of stochastic processes or models that violate those rules for normal diffusion. Here's a list taken from a review paper in physical chemistry and chemical physics, and what we see is that here is the normal diffusion stochastic process. It's called Brownian motion, and for this model, mean square displacement is a linear function of time, but then we've got all these other models for which the scaling rates are different. Go to some power, there's some logs in there, and in fact, some of them have scaling rates that are similar to one another or identical to one another, despite the fact that the microscopic particle motions could be different. And so it turns out now there's all these different methods that, based on the scaling rates you observe and some other statistics, you can really pick the regime in which you sit. The other thing I'll mention is you see the acronym CTRW mentioned a few times here. Continuous time random walks, I think, are the best known stochastic process that have been used in environmental applications. And there's a few different kinds of them, and they are listed here. All right, before I talk about the anomalous diffusion models, let's talk about the original application, the diffusion application, and what the originators actually did with it. Before the emergence of the two main players in this world, Marian Smoluchowski, who is a Polish physicist, and Albert Einstein, there were some experimentalists, Robert Brown and one other guy whose name is escaping me right now, who observed that small grains sitting in water seemed to be moving around on their own without being alive. And it was later that it was observed, and I'm reading this now, that those displacements were due to irregular thermal movements of molecules of the liquid. So there were random thermal fluctuations of molecules kicking around these particles. But the whole point here was these guys went through and derived the diffusion equation as something that governs the bulk motion of particles making certain types of movements. And by linking this motion with the statistics of random displacements and demonstrating this linear relationship between mean square displacement and time, both men independently derive the relationship between D, the diffusion coefficient, and the physical properties that drive it. So in this case, it was thermal energy, mass, and friction. And then if you go further to the right, the gas constant was well known at that time. And so using this understanding of how the dispersion coefficient is related to time, and by running experiments where they changed temperature and the mass of particles, they were able to describe or to actually calculate Avogadro's number. So kind of an interesting application, which was, of course, the first application of diffusive transport and the first time in which stochastic processes were used to link bulk particle motion and underlying microscopic motions. In environmental applications, of course, we don't have these underlying random thermally driven motions driving our particles apart. What we have is velocity fluctuations that arise from environmental heterogeneity. So as particles move on these paths, they tend to maybe diffuse normally, but most likely diffuse in some, or disperse in some subdiffusive or superdiffusive way. I need to pull up my clock. Oh well. So anyway, in hydrologic transport or geomorphic transport in each subfield, what we really want to get to is, number one, what drives the type of scaling that we might observe, or the physical controls on that alpha, and then of course, if we finally are able to get some kind of constant dispersion coefficient, what are the physical controls on that? And I will just mention now that when I put this on a log-log plot, now we have that the scaling rate is the slope and the diffusion coefficient would be a shift off of that. So how do we know when we have anomalous transport in the first place and we need to go to one of this long list of anomalous transport models? And really what it has to do with is all related back to the classic fractal example of measuring the coastline of Great Britain. So here, shown on the top square, is the classic example of one of the conundrums that one can run into with fractals. And that has to do with the fact that the smaller the ruler with which you measure this rough terrain, the more detail you pick up and the longer the coastline appears to be. The length of the fractal that we've got here depends on the scale of the ruler with which you measure it. We call that scale dependence. The analog for particles moving in heterogeneous environments, such as the Earth's surface, is that they follow fractal paths. These paths can be fractal in space, so a particle moving through some heterogeneous medium, or they can be fractal in time, where the time series of the points at which a particle moves is fractal. But the big point is, if you try to measure mean square displacement by looking for some linear relationship with time, it's like using a linear ruler on a fractal object, and you end up with scale dependence. And this scale dependence has long been known as, at least in the groundwater world, the scale dependence of dispersivity. And this same thing is seen across the various applications that I will talk about. It turns out, if you try to model anomalous diffusive transport with a diffusion model, D will not be constant, but a function of that with which you measure it, either the time or space units. So here's how we tend to use anomalous transport models. If I'm thinking about a new application for the first time, the first thing I want to know is, am I looking at long time average particle motion? Am I looking at bulk particle motion, like the spread of solute? Or am I looking at the statistics of individual particles, for example, in coarse sediment transport? In one of these areas, we can only measure things like scaling rates or bulk dispersion coefficients. And in that case, we're looking at ensemble averages, so the effect of the motion of lots and lots of particles. In sediment transport, we can actually track what the distribution of particle jumps is, whether things are correlated in time, exactly how long things have to wait before they get to move again. And if you're looking at the statistics of single particles, then we say we're looking at time averages. And I write this with different notation because we're going to get back later to whether you can compare these two quantities, or when you can and when you can't. And of course, the idea is, regardless of which kind of model, microscopic or macroscopic, you get from one to the other. So when you're measuring microscopic motions, what bulk particle motion might look like. When you can only look at bulk particle motion, hopefully you can go back to what the underlying microscopic motion that is related to physical processes is. And of course, when I look at these, I think about, okay, what is it that I can measure? How do these properties scale? What is D? I'm going to look at a few of these long list of applications in which anomalous transport models have been applied. The first one is at least the original one that I looked at, which is solute transport in porous media. I originally looked at it with my group, or I guess my dissertation advisors group, with respect to flow in groundwater systems. What we measure, of course, is breakthrough curves, or spatial snapshots of concentration once a slug of tracer has been injected upstream. Some of the signs of anomalous transport in this area, of course, as I mentioned, were the scale dependence of dispersivity, long discussed in groundwater textbooks. And we also see skewed breakthrough curves with late time tails, or snapshots with much earlier arrivals, say, than a diffusive model might predict. Many years of work in this field have really led to the idea that anomalous transport in porous media is related to, power law, or long time, or very wide resonance times of solute in immobile zones, which in ways is also related to correlations in the hydraulic conductivity and then flow fields of aquifers. Some of the drivers that have been identified for scaling rates are specific things like the distribution of the log hydraulic conductivity around preferential flow paths. And also there have been many studies, and I mentioned a few names down below. There are really a lot of them. I'm a little embarrassed I'm not mentioning them all, that talk about, what is the structure of a hydraulic conductivity field that produces specific scaling rates. The specific alphas that we might see if we were looking at breakthrough curves that have run through those fields. Flow in fractures. There's been some laboratory measurements, a lot of numerical studies of flow and solute transport in these systems has been identified as anomalous because of the time-dependent dispersion coefficient. There have been numerical studies in the last few years that have really identified small-scale eddies that form in fractures due to roughness or asperities that hold back solute as they move through fractures. And I looked at a paper the other day that talked about the alpha, that anomalous scaling rate, really being related exactly to the variance of a fracture aperture, and also a few other statistics of fractures. And in both the groundwater, in the porous media, and the fracture flow applications, D, which tells you about the magnitude of growth of transport, really has to do more with hydraulic parameters like flow rate, gradient. Okay, coarse sediment transport, I put a little asterisk near. It's unique for two reasons. The first is that it's one of the first applications I've dealt with where we're really looking at individual particle motions, not just bulk observations of what's happened in tracer studies. So because we can, look at we can track particle motions in flumes. There's even been studies where people have tagged tracers in the field using little radio tags or magnets. And then we can also measure exact particle residence times, in particular in flumes, by continuously measuring bed elevation. So this is a case where when the stream bed goes up, that is when particles are deposited. When the bed elevation goes down, that's entrainment of particles. The difference between those guys is residence time. And so here's an application where we can really where we can really track particle space and time contributions exactly. The other thing is there's a very nice history in sediment transport. Let me go to the next slide quickly. That goes along with the development of anomalous or actually of stochastic processes and stochastic transport theory in general. And that has to do with the fact that, as many sediment transport people know, Hans Albert Einstein, the son of Albert, got his PhD at ETH in Zurich in civil engineering, and he studied bedload transport, so sediment transport in rivers. And like all good fathers, Albert told Hans Albert that if you're going to be looking at this problem, you have to take a class in probability theory. And so Hans Albert took a course actually with the well-known mathematician and probabilist called Polya, and Polya was on his committee and helped him with his dissertation, which basically set up sediment transport in rivers as a random walk problem. Now, at the time, they did not have the mechanics to deal with power law velocity correlations or power law residence times, but Hans did mention early on in his thesis that bedload transport was really a particle motion and particle rest problem, or alternating periods of rest and motion, and that it was really important somehow that these periods of rest not be too long compared with the periods of motion. And so a bellwether of the need for anomalous transport. Bellwether, wrong word. Well, predicting the use of anomalous transport for this application. So, signs of anomalous transport. Observation of these really long particle residence times as sediment can vertically mix into the bed. And then also the observation that the virtual velocity, which is the average velocity of a particle from start until now, decreases as a power law because you start incorporating lots of zero velocity periods. And I will say that there has been a very rich development of anomalous transport theory around sediment transport. A lot of it has used alternative formulations which have been based on thinking about rates of entrainment of particles rather than the flux-based perspectives that we tend to use for solute transport. But we've been able to measure, observe, simulate different kinds of particle scaling rates that have to do with, or different anomalous transport regimes that are related to first the acceleration of sediment as it is first entrained in a river and starts moving into moving with fluid, correlated motions as sediment is transported continuously in a flow path without being redeposited, and then also the scaling rates that occur when power law rest times are incorporated into anomalous transport. Now, I mentioned before the difference between looking at ensemble averages and the statistics of individually moving particles, because in normal transport, we usually think that the ergodic hypothesis is valid. And that basically says that we think that the way things scale with the mean square displacement of lots of particles is equal to the time averaged, or the long time mean square displacement of a single particle. And it really turns out that this is true for normal diffusion, but not true for anomalous transport models. So here's that long table with all those different stochastic processes again, and I've expanded it. You can see there's a list, for each stochastic process. Is it ergodic? Well, for normal diffusion, it's yes, because the mean square displacement grows as time. The mean square displacement for a single particle in a long time also grows linearly. But as you can see, for most of these other processes, these two things don't match. And so you have to be careful to make sure that when you're trying to figure out what stochastic process you want to use and you have single particle trajectories, you pay attention to the difference between these two quantities. Another example, anomalous solute transport in fluvial systems. The history of this study goes back almost as long as we've looked at the same problem in groundwater, and that is that the breakthrough curves of a pulse of solute injected upstream has a very skewed breakthrough curve. So when we measure the downstream concentration profile, we see skewness and long time tailing, incomplete mass recovery, because it turns out there's still lots of solute that are visiting the hypereik zone or other transient storage zones, such that the residence time distributions tend to be distributed as these power laws, so violating the normal diffusion requirements. There have been lots of studies of different drivers of these power law residence times. For example, bed forms of different sizes induce exchange with different flow rates. The flow paths are different. The times it takes to get through different parts of the hypereik zone, different depths, sides of the channel, lead to various lengths flow paths in the hypereik zone, which are so slow compared to what happens in channel, or compared to flow velocities in channel, that we consider those as immobile zones where particles stop for these long periods of time. Same problem when we're looking at suspended sediment. We can measure suspended sediment concentrations using turbidity meters. It's long been thought that when we have input upstream due to changing climate and more erosion, or maybe mass wasting events, that we should be able to read those signals of inputs of fine sediment way downstream. But it turns out that, when you hit the wide parts of rivers where you have slow flow and really extensive floodplains, you end up with particles settling in those floodplains for, again, sometimes short periods of time where it's easy to be re-entrained and flow back in, or sometimes, tens, hundreds, thousands of year residence times where the time scales at which particles can be re-entrained are akin to those of the length of time it takes for a river to meander across that floodplain and remobilize sediment. Hill slope evolution is a little bit different, a different way of looking at things. So geomorphologists look at hill slope profiles and their time evolution and try to understand the type of deposition and erosion processes that have to have occurred in order for the profiles that we can measure to emerge. The signs of anomalous transport, more than a scale dependence kind of thing, have more been the poor fit of profiles or the time evolution of profiles to local or nonlinear alternative models that have been proposed. But recently, and I'm going to call out Tyler Doan, who's a graduate student at Vanderbilt working on his dissertation right now, who I think is the first to actually observe evidence of non-local transport on hill slopes in the field. He's been looking at lateral moraines on the east side of the Sierra Nevada and demonstrating that particle entrainment rates and travel distance are not simply functions of local slope, so not simply functions of what happens, right a few inches around that spot, but can be, but anomalous transport models need to be invoked in order to deal with the fact that vegetation and other types of barriers act as sediment capacitors on hill slopes, allowing them to oversteepen and then suddenly release lots of transport in one event. Also, there's the fact that there are various transport processes that act over different scales of the hill slope. We have pore scale creeping processes, freeze-thaw, rain splash. We have burrow scale sediment transport that occurs, and entire slope scale transport that occur, all of which that lead to the need for non-diffusive models to describe both the way sediment moves down hill slopes and what the resulting hill slope shapes look like. The last application of anomalous transport I want to talk about is one of my favorites. It's the generation of stratigraphy. As Diogo mentioned, I've strayed a little bit from hydrologic processes, but one of the reasons that I really like this application is because it's one of the times where anomalous transport can almost go in air quotes. There's nothing like showing air quotes in a webinar, but I'm doing little quotes in the air here. It's not transport of particles in the classical sense, but transport of a point on the Earth's surface as it moves up and down due to erosion and deposition. So on this graph here, we have time and thickness of sediment, or you think of it of elevation of a surface. And in time, we have the elevation of the surface moving up. Maybe it moves up and down more, but then due to erosion, some of that disappears. And so what we have is the sediment surface transporting up and down. This movement can include some kind of advection due to external forcing. Usually, well, it's thought there has to be generation of accommodation space to say for there to be overall deposition due to, say, climate, tectonics, change in base level. But the point is, as sediment transport tries to smooth the surface, there are all these up and down fluctuations that we conceptualize as following the same kind of statistics as dispersing particles. Interestingly, this meant that the measurement of accumulation rates in cores was subject to some kind of scale dependence. This is actually called the Sadler effect. Instead of scale dependence of dispersivity, this is the name in this area is the Sadler effect. A very incomplete geologic record due to this process I just demonstrated means that cores, outcrops tend to have power law periods of missing time. When accumulation rates are measured with a linear ruler, like you say the difference in depth of 2 points that you could date in a core over the delta t, you're using a linear ruler, that rate tends to be proportional to the temporal measurement interval over which you make it. I know I said this rather quickly, but the analog is really a decrease in the apparent or virtual velocity of sediment or solute subject to power law residence times. It's just that in this application, measuring that mean value is something fundamental to the study of that process. Let's see, what's interesting has been that the drivers, I mentioned that anomalous transport here comes to an incomplete geologic record, and some of the drivers are actually long-range correlation and anomalous sediment transport that occurs across a fluctuating Earth surface that leads to the power law periods of missing time in cores. And gosh, I should really put in a reference here. That would be Schumer 2017, a GRL paper that came out a couple weeks ago. Anyhow, as I finish up, I'm going to address two topics. First, a non-exhaustive look at how the study of hydrologic anomalous transport and geomorphic transport has impacted the field. And also, as Diogo requested, some thoughts on why anomalous transport has not gone mainstream. First, in the cases of fine sediment or solute, it's become apparent that the form of the residence time distribution is key to predicting overall transport, as well as the fundamental controls on transport. And there's really now an entire field. I just was reading papers from a special journal issue related to travel time distributions, how to measure them, how to interpret them, and how the hydrologic state of a system affects those residence time distributions. We know, of course, that transport is a control on reactions and nutrient processing. The models required for various types of reactions coincident with anomalous transport represent a generalization of reactive theory in itself, anomalous to the magnitude of having to redo transport theory. Part of it is there's strong coupling between transport and reactions. And that makes the theory a little bit more complicated, and I'm pretty sure that one of the upcoming talks in the Kawazi webinar series will go into depth in that topic. Next, if I could go beyond 45 minutes in this talk, what I would definitely include next is a discussion of the length and timescales at which anomalous transport models are applicable, and how and why there can be an eventual switch to normal transport would be the next topic included. So another important thing for you to think about as you get into this area. Finally, in addition to the rich analytical theory that underlies anomalous transport models, is how to implement them numerically. Suffice it to say, when we start dealing with non-local, which means transport subject to action at a distance in time or space, the numerical algorithms and the implementation of boundary conditions and initial conditions becomes a lot more complicated, and there are many groups working on those problems. So, let's see. Why hasn't anomalous transport gone mainstream? And in addition, I would like to I hope that during the question and answer period, more of us can discuss it. Actually, let's start with number 5. I don't think that there's much material akin to, well, we start with this equation for flux and we plug it into conservation of mass and then we get this equation. It's taken a long time to nail down the underlying theory. I think we're at a point where we're ready for that, but you can't find textbooks that explain this stuff. There are a number of tools out there like the CTRW toolbox. It comes out of Brian Berkowitz's lab, and now the FracFit tool for fitting fractional advection dispersion equations that are used for some anomalous transport models, and that came out of Mark Merschart's group, that are pretty easy to use without an in-depth knowledge of probability theory and stochastic processes. But the easy-to-use tools don't go much farther than that. I mentioned non-stationarity because in looking at reach-by-reach tracer studies in rivers, say, it's not clear to me that scaling rates really stay consistent as you change geomorphic regimes. So I think that, upscaling studies that are easy for people to understand and then apply themselves haven't really been produced. And then 1, 2, and 3 are sort of the standard answers that you might hear. Oh, if we discretize our models finely enough, we can capture enough heterogeneity that we don't actually need to use analytical models for heterogeneity. There are many people who are really opposed to the use of, well, if you add an extra parameter, of course you're going to be able to fit this transport model better. The argument here, of course, is that if you're using too few parameters, you find this scale dependence problem. And also, I think that as we, find new applications where we need to use anomalous transport models, we're still in the discovery phase of figuring out exactly what the physical drivers are for the different scaling rates. So I will basically stop there. In summary, I will repeat that in hydrology and Earth surface applications, normal transport is not the norm. You should expect to see anomalous transport. And the reason has to do with the fact that particles in heterogeneous environments are basically making fractal paths, and their properties will appear scale dependent if you try to measure them with that linear diffusive ruler. There's a few different ways that we approach these problems. In some applications, we can measure bulk properties of transport only, and we have to go back and figure out, using our expertise, what the physical drivers of anomalous transport are. And then there are some applications where we can do single particle trajectory analysis and get those, figure out those statistics simply by measurement and interpretation. State of the art is still figuring out what alpha is and what drives D. And I think as we will see in some of the future talks, this has implications on risk for groundwater management, management of other systems, rivers, and also for how we describe reactions and processing. So there you go. That's what I've got. Here is a list of the upcoming talks, and I will turn it over to you guys for questions now.
If anyone has any questions, please type into the chat box and we'll read it out loud, and then Rina will answer your questions.
Liz, do I see a chat box?
It should be towards the bottom of your panel.
Yeah, I can see one here as well.
I cannot, so someone's going to have to read it to me if there's any questions.
I'll read them out as they come in.
Okay.
If any are going to come in.
Oh, come on. Is it too easy of an audience? Or too hard an audience? One or the other.
Well, while we're waiting for questions, I'm going to take back your presenter mode and send it so I can show my screen. All right. Looks like we have some questions.
I can't actually see any questions. So Liz, if you see them, can you read them out, please?
Yeah, of course. So here we go. The first question asked, Ralph Metzler, given the non-universality of anomalous transport, could the lack of going mainstream also be connected to the very recent direct evidence of, say, power law retention times from single particle records?
Oh, I wish I could read that question. Say it again, please.
Given the non-universality of anomalous transport, could the lack of going mainstream also be connected to the very recent direct evidence of, say, power law retention times from single particle records?
Yeah, I mean, that's part of it. This is all really new theory. And, you know, unlike, I think, the early equations that were used for groundwater and contaminant transport, where there was really instant technology transfer from other fields, these are being developed hand in hand now with what's going on in, say, you know, your area, you know, with the theorists who are creating the theory as we go.
All right. We'll go to the next question. I'll paste it into the chat box here. It's from Jingfang Wang. Excellent talk. Could you give an example of problem can only be solved using the abnormal diffusion constant method?
Read that for me one more time, please.
Could you
Examples
give an example
of equations?
Of problems that can only be solved using the abnormal diffusion concept and method?
Okay, well, yeah, so in order to stay away from jargon, which could go on forever, I didn't talk about exactly what the equations are. If you look at the continuous time random walk has been the most popular model that has been used in environmental applications, and that's one in which you can define travel distances and travel distance distributions, waiting time distributions, plug it into one of these master equations. And then there's a model that is actually can be fit. That's what you see in the CTRW toolbox. Or if you take, under certain cases, when you take these limits, you can end up with things like fractional advection dispersion equations or partial differential equations with time-dependent diffusion coefficients that go along with these models. And in lots of the papers that I mentioned, the derivations of the equations are all in there. That was just the part that I felt like I needed to skip in order to get the concepts across.
Okay. Next question is from Sarah Godsey. Can you expand more on the correlation between flow fields and hydraulic conductivity fields and the relation to anomalous transport?
Sure. Well, in one of the, hey Sarah, in one of the papers that I referenced up there, numerically what was shown, and I believe this was a Brian Berkowitz group paper, was that, first of all, particles really only move through a small fraction of, say, a porous medium. And if you look at those preferential flow paths, if in fact you create if you create a histogram of the different conductivity values and weight it by where the particles actually go, these power law residence times show up as particles are driven through preferential pathways and slowed down in the low K pieces of them. So that paper there actually links the distribution of the log conductivity field within those flow paths, and it's those slow places that dominate and hold particles back for the longest, create some correlations in the velocity field and the power law waiting time distributions.
All right, next question is from Shane Putnam. How might ideas of anomalous transport be incorporated into models like parflow or hydrogeosphere, parentheses, discrete element process-based? Would it be setting the parameter alpha and D for each land use type?
Well, an interesting question. So one thing that is really has come out of the theory that's really interesting is that some of the solutions to anomalous transport models are transforms of the solutions that come out of normal diffusion models. That being said, and my colleague Boris Boehmer has done a lot of the analytics and numerics that go along with this, there are cases where you can take, say, the output flow field from ModFlow or whatever transport model you've been using. You can take that velocity field, and you can you can run particles through it. So then get the output from, let's say, MT3D or some transport solution. You can take that output and actually just transform it in a way that allows either what we call subgrid heterogeneity or power law waiting times to be incorporated into the solution. So that would be a great, simple way to go if we're just looking at sort of big scale. In terms of really just having numerical models that solve these equations, that is a much bigger task, given the computational power. If there's anyone out there who's, there are folks who have started doing this. If anyone wants to address that, feel free. It's a little bit outside of my area of expertise, but I really do love the transform ideas.
All right, any more questions? All right, it looks like there are no more questions. So I'll just show you guys a few slides. The next, oh, hold on. One from Paula Cedillo. Can abnormal diffusion cause problems when estimating nutrient uptake metrics?
You know what? I am going to punt that one to Antoine Aubonneau, who will be giving the next webinar. And I would say that he right now is our expert in solute transport in rivers and how to deal with biogeochemical processing. So yes, it's all part of, dealing with reactions. And I think that's just starting, but I think that is a wide open area for people to work on.
All right, next question is Siwei He. For the anomalous modeling, do you solve Fokker-Planck equation or traditional conservation equation?
Let's see. I'm going to try to interpret that question. So what happens is you have master equations which describe the probability of how particles can get to each possible location. So given that a particle started at 0, what steps did it take to get to where it is right now, and what's the likelihood of a particle making those steps? Those master equations or Kolmogorov-Ford equations are you plug in statistical assumptions, and then you take limits and you arrive at Fokker-Planck equations. The solution to the Fokker-Planck equations are things like Gaussian shapes or other skewed shapes that are the solutions to, say, the diffusion equations. So if there's more clarification you need, I might not be answering your question correctly, but the idea is that you are first deriving these conservation equations, plugging in statistical attributes for jumps and waiting times, taking some kind of limits, and then getting to these governing equations.
All right, any more questions? Doesn't look like it, so I'll bring everyone's attention. Next Friday, Antoine Aubonneau from Purdue University will be speaking on linking freshwater transport and quality on New Frontier. All talks take place at 3 o'clock Eastern time. And then also bring attention to everyone's There are 2 deadlines coming up for Quasi. We have Instrumentation Discovery Travel Grants. Travel grants to visit colleagues to learn new instrumentation. We offer up to $1,000. Graduate students, postdocs, and faculty members are eligible to apply. The deadline is April 1st. And then we also have a conference on hydroinformatics. The theme is Swimming in Data Without Drowning in Deluge, and we are currently accepting abstracts, and you can submit it up until April 15th. All right, I think that is it. So thank you everyone for attending the webinar. Hopefully we'll see you next Friday.
Yes, and I hope everybody's clapping, even if Rina can't hear it.
Air claps.
Rina, thank you very much for this talk. Look forward to seeing you all next week.
All right, thank you everybody. Bye.